Okay, screencast 15.2, let's learn a little bit about water. We're talking about acids and bases, and you really can't talk about acids and bases without thinking about water. We will consider what's the structure of water. You've learned in the previous slide that an acid is H plus and a base is OH minus. It might be important if we're thinking about water. Let's think about it more deeply. Is water an ionic substance, or is it a covalent substance? Or is it a little more complicated than that? How do we show this interconversion? I'm giving away, I suppose, the answer to the previous question, but how do we show this interconverting nature of water between multiple different forms? And how do we describe it quantitatively? I mean, is it mostly one thing or is it mostly another? I mean, come on, I thought water was simple. And finally, let's think about how that related to what became known as pH. What's up with pH? What does it mean? How does it relate quantitatively to what water is and what it contains? Okay, so let's go ahead. What is water? I'll bet you know that water is H2O. Most people do. You learned that a long time ago. That's the same as HOH, since oxygen always has two bonds and hydrogen always has one. Let's go a little deeper. Is it that HOH form, or is it maybe H plus and OH minus? In other words, does it favor the covalent form, or does it favor the ionic form? If you're asking which one is it, well, the only real answer is that it's both, because it is a little bit salty, if you will. It does have some of this. It's a measurable amount, but boy, is it a low amount. Here's what's going on. You've got that nice covalent form of water. There would be no pH or no acidic or basic component if that's all it was, because there is no H plus, there is no OH minus. However, there's a measurable equilibrium here where this is interconverting between these two different forms, the covalent and the ionic form. It drastically favors the covalent form. You really can't taste water as all that salty, can you? Okay, they measure these things. They came up with a convoluted system where they call it an equilibrium constant. It gives you an idea of just how much of this you have compared to this. And if you measure the concentration of this, multiply it by the concentration of that in a solution, you'll find that it's a super low number. They call that the equilibrium constant for water, and it's only 10 to the minus 14th moles per liter. So if you have a liter of water, you have a total of 10 to the minus 14th molar solution here, and we're multiplying these, so you have 10 to the minus 7th of this and 10 to the minus 7th of that. By definition, these get multiplied. And that's a super low number. And in water, if it's pure, it's not acidic, it's not basic, it's neutral, since there's equal amounts of H plus and OH minus. And that must mean they're each 10 to the minus 7th moles per liter. And if that's true, we could say that. Well, you know, the concentration of H plus is 10 to the minus 7th moles per liter. Yuck. People said, why don't we just call it pH 7, where pH stands for powers of hydrogen. Really, it's negative powers of hydrogen because it's not 10 to the 7th, it's 10 to the minus 7th, or 1 over 10 to the 7th. In any event, they decided to use this pH scale rather than simply describe the concentration using just a regular number, 0.0000001. That's 10 to the minus 7th. And if you have a pH less than 7, you have an extra amount of H plus, and that would be an acidic solution. If you have an excess of OH minus, you'll have a number where the H plus is less than 10 to the minus 7. And that means the pOH is greater than 10 to the minus 7. In any event, if the pH is greater than 7, that means it's basic. Okay, that's a little bit about acids and bases.